The answer is. This is as n goes to infinity, right? You think it goes to 1? I mean, this gets infinitely big, right? But what does this go to? It goes to 0. So they're doing battle against each other, right? And you don't know which one's going to win. So you think it goes to 1?
Yeah.
What did you do to try to prove that?
I changed it to be sine of 1 over n over 1 over n.
Ah, so you did the limit as n goes to infinity of sine of 1 over n over what? 1 over n. I like that. So then you just cancel this and made it sin? No, you can't do that. Okay. What'd you do?
Remember, I said it went to L'Hopital.
Can you?
Yes.
It does work?
They both go to 0.
They both go to 0?
Yeah.
Okay, so if you apply L'Hopital's rule, I like this. Cool. The derivative of sine of 1 over n is going to be what?
Cosine 1 over n.
What's going to go? Careful. What do you have to use? You have to use the chain rule on the top.
Yeah.
Oh.
Cosine 1 over n.
Oh, you put it at the end. Okay. Cosine 1 over n. Okay. Times what?
Natural log of n.
No, not natural log. What's the derivative?
Oh yeah. Never mind. 1
Negative.
Over negative 1 over
Negative n to the all over.
Negative n to negative 2. It cancels anyway.
Negative n to the negative 2. Is that correct?
Yes.
That seems pretty good. Okay, so now you want to cancel? So now we have the limit as n goes to infinity of cosine of 1 over n. What's that going to go to? Cosine of 0, which is 1. Good job. This is kind of something I remember seeing before, and I just don't really like it. I think your way is much better than what the book is. I'm about to show you what the book does.
Okay.
This right here is exactly the same as saying the limit. Let's say x equals 1 over n. This is the same thing as x going to 0 of sine of x over x, which is 1. You remember the squeeze? You proved that in maybe the first. I think you probably proved that with Mr. Grasso. Exactly, right? It's the same thing. Changing things like this behavior is the same in each place. So you just kind of normalize the behavior by saying x equals 1 over n, but then you have to change it to x going to 0. I like your way a lot better. Which does this. Anybody have any ideas about what to do? Make it a limit. Okay, so yeah, the limit as n goes to infinity of sine of 2n over 1 plus the square root of n. The problem here is, what's the sine of infinity? What's it do?
It just goes around. So I use squeeze theorem.
Ah, you use squeeze theorem. How did you apply the squeeze theorem here?
Negative 1 is less than sine of 2n.
Ah, okay, so you did it like this. I like what you did. So limit as n goes to infinity of sine of 2n, right, times 1 over 1 plus root, like this, correct? And you know that the sine of 2n has to be less than or equal to 1, but greater than or equal to what? Negative 1. So now you multiply everything by this right here. So you're taking this and you're tacking it on to all three. So what do you end up with? Negative 1 over 1 plus root n less than or equal to 1 over 1 plus root n times sine of 2n is less than or equal to 1 over 1 plus root n. And you know that if n goes to infinity, this goes to 0, this goes to 0, therefore by squeeze equals 0. That's great. Good job. You can either have increasing, decreasing, monotonic like this, or non-monotonic would be something like that. If it stops for a second. Because this right here means it can't be increasing, right? Because it's staying the same. So here's the deal. If it's always going up, this is increasing, always going up. If it's always going down, it's decreasing. If it stays the same, it's monotonic. But if you add them together, if you add increasing plus monotonic, what do you get? Not monotonic. Yeah, it's annoying, I know. Okay, on the record now, totally got this wrong. I thought monotonic was stayed the same. Not. Wrong. This, if it's either increasing or decreasing, it means it's monotonic. monotonic is either one, because the definition, which I totally got wrong, is right there. If it's either increasing or decreasing, it's monotonic. It's doing the same thing. So monotonic equals just increasing or just decreasing. So, but my example of not monotonic is still holds. Not monotonic. Monotonic. Anything else.
So it completely level.
If it goes up and level, like this.
Or if it's just
Up and level. That's not monotonic. X squared, because it goes down and then up. Because that's not increasing or decreasing.
So everything that is also monotonic.
Correct. Ready? Like this. Ready? Ready? No, because it's not increasing. Like this. You can think of it like this. These are all the monotonic sequences. That you have increasing and you have decreasing.
Everything else is not monotonic.
Correct. Sorry. What can you do with that?
It just makes.
Yeah, you look at the absolute value. So you do the limit as n goes to infinity of the absolute value of an is the same. If it goes to 0, it also goes to 0. If this goes to 0, then the limit as n goes to infinity of a to the n equals 0. So what we're going to look at is the limit as n goes to infinity of the absolute value of this. And it's nice doing that because basically what do we get to drop entirely? Yeah, it's just the limit as n goes to infinity of n over, well, yeah, because it's always positive, plus 1. And what's that going to be? You don't need to, don't. Stop using L'Hopital's. You could just do that at this point. Yes, you could do it all the way out and say L'Hopital's rule, but at this point you could just say the bottom is definitely going to be infinitely, not infinitely, but much bigger. But yes, you could use L'Hopital's rule and get the limit as n goes to infinity of 1, oh no, don't be, of 2n. And then you could say that's equal to the limit as n goes to infinity of 1/2 times 1 over n. And then you could say that's equal to 1/2 times the limit as n goes to infinity of 1 over n, which we know in fact is equal to 1/2 times 0, which is 0. So there's a limit to how detailed we want to get. Do you see what I'm saying?
Yeah.
You can bail at this point. You can just say it's equal to 0. Okay? That's fine. Okay, put everything. Okay, so do you hear me talking? I mean, is it just a key to you to start? Okay. No, it didn't, thankfully. Okay, so here we go. So you're looking at, you're doing -3 an equals -3 to the n over n factorial, right? So we're going to examine the limit as n goes to infinity of the absolute value of this thing, right? We want, because if this goes to 0, we know that the original one goes to 0, exactly. So because of that, because there's an absolute value, what do we get to drop? The negative, right? So you have 3 to the n over n factorial. So written out, what does that look like? Well, it's the limit as n goes to infinity, and what are we going to have? 1 over n. Well, we can do it in any order we want, but let's do it in descending first so it makes sense. You have 3 times 3, how many times? Keeps going, right? And then on the bottom you have n times n minus 1 times n minus 2 times. Keeps on going, right? Just keeps on going all the way down to 1. Yes, you're correct. That's good. Okay, so I'm going to do a little bit of reorganizing and see if you can see what's going on. So you know the limit as n goes to infinity. I'm going to pull out this 3 over n. That's going to be our heavy operator, okay? I'm just pulling that off the front. You see where I'm getting that from? There it is. Then I'm going to, just so you can see it, I'm going to take the rest and I'm going to put it in a different order. It's going to be 1 over, if I flip it around, what's it going to be on top? It's always 3. So it's going to be 3 over 1 times 3 over 2 times 3 over times 3 over times so forth, right? All the way up to 3 over n minus 2 times 3 over n minus. Do you agree with that? Okay. So what can you tell me about this term? Is that greater than or less than 1? I'll answer the questions that I am asking you. That would be helpful, okay? Is that greater or less than 1? It shouldn't be a super complex. Oh, it's less than. So what can you tell me about all of this? Less than 1, right? Do you agree with that? So what can you tell me? Therefore, what can you say? If you can now say the limit as n goes to infinity of 3 over n times, it's less than that times 3 over 1 times 3 over 2 times 3 over 3. Do you agree with that? This thing right here makes the thing smaller, right? It makes it smaller. So if we were to drop that away, we just made the whole thing a little bigger. We just made it a little bigger, but we just made it easier, right? Because what does this thing go to right here? 27 over 6, right? Which is just going to be 9 over 2. So now we have less than or equal to 9 over 2 times the limit as n goes to infinity of 3 over n, which is going to be 9 over 2 times 0, which is 0. The key realization, and you can do this in different ways, is that this right here is less than 1. It is less than 1 because each term is less than 1. When you multiply a lot of things together that are all less than 1, what do you get? Something that's less than 1. I mean, technically speaking, it's important to note that this thing is less than 1 and greater than 0. It's important to note that. That would be good. Or you could construct series or infinite sequences where instead of having commas between all the terms, we have plus signs. Again, n is going from 1 to infinity in its natural numbers, not fractions. And we're adding them together. And that's what this little summation means. Why is it okay to write it without the n equals 1 to infinity sometimes? Because if it's not there, it's implied. Exactly. It's like not why we don't write the first power. If it's not there, what power do you assume is there? 1. If it's not there, you assume n is going from 1 to infinity. You are literally going to write this 1,000 times in your math period, and you're going to understand why they dropped it. Okay, so there are many series that follow this pattern right here. You have a first term, and then the only difference between the terms is you're multiplying it by a constant. What are you multiplying it by? R. A1, A2, A3, R. So this is A times R to the n minus 1. A times R to the n minus 1, right there. Great. This is really, really, really common. You're going to look at this all the time. You're going to take things that don't look like this. It turns out they are this, and you're going to know a lot about this form right here. Okay, let's see if we can figure it out. And I'm going to give you a little bit. A plus AR plus AR squared plus AR cubed plus ... And what's it going to? AR to the n, right? We're going to add it all together. Do you agree with that? And that's going to be equal to the sum of the first n terms. Do you agree with that? Okay. RA plus, let's not change the order. What do we get? AR plus AR squared plus AR cubed plus AR plus ... plus AR to the n plus 1 equals R times what? R times Sn. Yeah. What's wrong?
The first one should be AR to the n minus 1.
AR to the n minus 1? Wait, what?
Because
all I did was multiply all of these by R, right?
No, the first one was written wrong.
The first one.
AR to the n minus 1.
AR to the n minus. Oh, right here. You're absolutely right. Thank you. To the n minus 1 like this.
Yeah.
Good.
So then you just get
A minus AR to the n is equal to Sn minus what? Correct? What can I factor out? A1 minus R to the equals. So what does Sn equal? Sn equals A over 1 minus what? R. Okay, so we just got to the really, really cool thing right here. So again, now we're looking as n goes to what? As n goes to infinity. Where's the only place n exists in this whole thing? It's right there. Let's assume for a second, R, the absolute value of R, is less than 1. If that's the case, what's the limit as n goes to infinity of R to the n? 0. So if this is the case, case 1 is the absolute value of R is less than 1. What does this become? Sn is going to be equal to A over 1 minus R, right? What's case 2? The absolute value of R is greater than 1. greater than or equal to 1, greater than or equal to 1, what happens then? This. Remember what ASN is? You're absolutely right that it doesn't make sense right there, but what was this equal to? A plus AR squared all the way up to AR to the n minus 1. If R is equal to 1, SN is going to be equal to A plus A plus A equals NA, right? And it would be divergent as n goes to infinity. So there it is right there. It's this really cool maneuver of you create something new, subtract it, and then, oh, look, all those things go away. In order to take an infinite number of things away, you're going to have to use an infinite number of things. This is just a cheap trick. Okay. Find the sum of the geometric series. So it's telling you to find the sum, so it's definitely going to be, it's definitely going to converge. If there is a sum, it's going to converge to something. So since it's oscillating, you know there's going to be a negative 1 to the what? To the n minus 1. That's going to be part of it. I totally agree with that. Totally agree. How could you simplify this if you wanted to analyze it to make it a little easier to analyze? What could you pull out of each numerator? 5, and that turns into 1 over 2/3, 4/3. Is that correct? Did I do that correct? Oh, 4/9. 4/9, and you're absolutely right. This is the 27, right? Like that? No, what else could I pull out? Well, we can leave it like that, okay? Okay, so the sign is flipping. So we need to actually write this as, does it look like a geometric series? Oh, it is, because it tells us it. What's the ratio going to be? Or you could just say, what do you multiply each one of these by to get the next one? Negative 2/3. You can incorporate this entirely just by making it negative 2/3, right? So it's going to be it's going to be 5 times negative 2/3 to the what power? N minus 1. Does that work? Plug in 0, what do you get? 5. Plug in 1, what do you get? Negative 10/3. Does it suddenly work? So now we're looking at, so our first step in finding this geometric series was to write it properly. So now we've written it properly. Now we're looking at the sum as n equals 1 to, I could not write it in, but I'm going to, of 5 times negative 2/3 to the, what was that formula we had right here? Oh, we can keep the 5 in there and keep it with the formula. That's fine. The 5, hold on. Like this. There it is. Is that correct? Yeah. So in this case, A is 5, R is, so what's this going to be? It's A over 1 minus R. So it's 5 over 1 minus 5 over, which is going to be done. How do we do that one? Let's just write out some terms, okay? When in doubt, write it out. Let's write out some terms. So when n equals 1, what do we end up with? 2 to the 4th. So 2 squared, I'm thinking of 2 squared times 3 to the, so that's going to be 4. And then n equals 2 is going to be 2 to the times 3 to the negative 1. I can't do basic math today. So what's that going to be? 16 over 3. And then n equals 3 is going to be 2 to the 6th times 3 to the, so that's going to be 8 times 8 is 64, right? Over 9, right? So what is does it look like this is a geometric series? Yeah, how'd you get from here to here? I multiplied by, here to here. So it looks like this thing is going to be 4/3 as the ratio. But what's the first term? 4, correct? So 4 times 4/3 to the what? There it is. Let's see if that works. Plug in 1, what do you get? 4. Plug in 2, what do you get? 16 over 3. Plug in 3, what do you get? 64. Does it work? Yeah, it does work. So what is this going to be? 4 over 1 minus. So it's going to be 4. Oh.
But R is bigger than 1.
Oh, wait a minute. Look what just happened. If we do 1 minus 4, what's it going to be? Oh, wait a minute. R is greater than 1. Divergent. Yay. Good catch. Hey, at least it's telling you it's convergent. That's nice. So, what should we do first? What did we do on the last one? Just write it out. 1 over 2. N equals 2. What's it going to be? What's it going to be? Yes, you could do it as, that's overkill in this case. 1 over what? 6. And then n equals 3. 1 over 12. So what does it look like we're going here? 1 over... Is it 3? Ooh, so hold on. Let's do another term and see what happens. So n equals 4. What is it going to be? 1 over 20. Now here's the thing. Is it geometric? Does it look like it's geometric? Well, look, we multiplied by 1/3. We multiplied by... what's going on? We notice, okay, sad, not geometric. So what are we looking at again? It's the sum of n equals 1 to infinity of 1 over n times what? N plus 1. Does that look like anything we've done before or structurally? Yeah, I just expanded it, so what am I going to want to try to do? I'll give you a hint. What's that stand for? Partial fraction. So what do we want to do? It's a over n plus b over, and we know that a over n plus b over n plus 1 has to equal 1 over n times n plus 1, exactly. Yay! So if we did, and then we know that another magic value is n equals, so a times 1 is equal to 1, so what does a equal? 1. So now we're looking at the summation of, not I, sorry, n equals what? 1 to infinity of, what was it? A was 1, so it's 1 over n minus what? 1 over what? N plus 1. Nice. Nice. So now at least we've broken it apart, and it seems like maybe this will help. Maybe. So at this point, my first step, Fawn, would be to actually look at the terms and see if I notice anything cool going on. Does that sound okay? So at first, though, you might think to yourself, okay, I'm going to do it in 2 different sums, right? But what do we know about 1 over n as you sum? What's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5? That what? That diverges. We haven't proven that, but it does, right? But then we're taking something away. So what happens? One of them is diverging, and one of them might be... Oh, okay. Let's just write out the terms and see if you can see it. If n equals 1, what is this equal to? 1 minus what? Minus what? 1/2. Oh, sorry. I'm writing this 2 things at once. If n is equal to 1, what's our term? 1 minus 1/2. If n is equal to 2, what do we end up with? Minus 1/3. And if n is equal to 3, what do you end up with? Minus 1/4. And what are you doing with all these terms? You are adding them, right? What happens? Boom, 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 boom. So what do you end up with? Basically, it's 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3, right? Not 3. Plus 1/3 minus 1/4 plus 1/4. So all of these are going to go away, and it's going to be it's going to be plus at the end, plus what? 1 over n. Is it minus? Oh, it's always going to be minus. Yeah, it's going to be minus. It doesn't change the answer, but yes. Yes, it is. Good catch. Yes. Minus n plus 1. Good job. But Again, I was being sloppy because I was like, oh, it's going to go away, right? You're looking at now, it's the limit as n goes to infinity of 1 minus 1 over n plus 1, which is 1. It's 1. You got to the prize. Take the prize. What you would do with this. So if you just take a calculator and start summing this, you'll notice that it keeps on getting bigger, and it doesn't seem to be slowing down. The problem is its rate of growth slows down, right? So you think to yourself, well, these are getting smaller, so it must converge. I've already told you, does this converge? No, it doesn't. Again, let's not break it down, okay? S of 2 is going to be 1 plus what? Do you agree with that? Let's just skip to S of 4. What is S of 4? That's 1 plus 1/4. Do you agree with that? Let's simplify that a little bit. How many 12ths? We need a common denominator of 12, right? So it's going to be 12 plus 6 plus 4 plus 3 all over what? 12. And what is that? 18. 18 plus 7 is over 12. What is that equal to? 2 and what? 1/12? 2 plus a 12. Okay, well we just crossed over 2, right? You agree with that? Doesn't approach 2. Okay, I'm just fishing out here. Let's do S of 8 and see what happens. Well, that's definitely going to be 2 plus a 12th, right? Plus 1/5 plus big numbers, right? That's it's nice. Okay, that's good. Dude, what is that in decimal form? Why did you really kind of like this? When you saw this, what did you immediately see, Andrew? You said that I circled that, the 2 plus a 12. What did you immediately say? I'm going to give some space here. Not 2, right?
Yeah.
Remember you said it's greater than 2, right? That was the important realization. Oh, it cleared 2 all of a sudden, right? So I'm going to change something a little bit. Let's just look at this right here. And in particular, I'm going to look at this right there. Is this true? Is that true? S4 has to be greater than that because what did I change? No, I made 1/3. Did I make it smaller or bigger? I made the right side smaller, right? I made the right side smaller, so that means S4 must be greater than that. Why did I do that? Well, what does this equal? This equals 1 plus a half, which is 1 plus 2/2, which is 2. We know it, which we already know. We found out what it was. Don't pack up yet. I want to give you one more iteration of this, and then we get this, correct? What you can end up doing, if you skip over here, if you skip to the next parts right here, so we know that S, if you want to write S sub 8, do something similar to S sub 8, and you'll end up with creating a pattern. You'll end up creating a pattern with halves. That's really cool. It's a squeeze out theorem. I like that. That's really good. I like that.